Yeah. Is my screen visible to you?
Yes, ma'am.
Yeah, thank you. Yeah, I'm Dr. SRILATHA Chebrolu, Assistant Professor in the Department of Computer Science and Engineering, NIT Andhra Pradesh. Yeah, today I would like to give a lecture on principal component analysis. The books that I am referring to are Principal Component Analysis Videos Lecture by Jose Starmer and Principal Component Analysis Second Edition by IT Joliffe. It's a Springer publication. Yeah. So principal component analysis, where it is used is given a very high dimensional data. High dimensional data in the sense there will be a lot of features will be there. A lot of features like millions of features will be there. Millions of features. Yeah, in that cases, when the data set has got high dimensions, in that case we use PCA. It's an algorithm, PCA, principal component analysis algorithm, to reduce the dimensionality. Reduce the dimensionality in the sense we will be finding a what to say, feature extraction kind. This is a feature extraction algorithm. We will be finding new features. Okay, so how we will be doing that and all we will see. Okay, the central idea of principal component analysis is to reduce the dimensionality of a data set. Dimensionality in the sense the number of features, okay, consisting of a large number of interrelated variables. Okay, interrelated variables in the sense there will be some relationship between these features. We can say variables, features, dimensions, or columns for that matter. Yeah, all are the same. Variables, features, dimensions, all are the same. Okay, there may be some interrelation between these features. Okay, so it is used for reducing the dimensionality of the data set while retaining as much as possible of the variation present in the data set. Variation, what is variation? Variation, let us take your marks. Okay, your some subject marks out of 100. Okay, some marks, it's a random variable marks. Let us say that marks is a random variable and we will be getting some distribution, right? Let us say 100 students marks are there. How usually it will be, these marks will be following some Gaussian distribution, right? Gaussian distribution, I mean, not all the 100 students will get the same marks, isn't it? It will not happen, right? So usually marks and all will be following some Gaussian distribution, that is the bell curve. Okay, so that is a variation. Variation in the sense there is some variation between one student mark and the another student mark, right? So that is called the variation. So when we compute the mean, average value, mean means the average value of these marks. So from this mean, how much each student marks is variating. Okay, that is called the variation. Okay, so we have to reduce the dimensionality. But still variation has to be preserved. It should, all marks should not go, and we should see that the same variation will be followed in the new data set. New data set in the sense a reduced data set. Okay, so yeah, and this is achieved by transforming to a new set of variables, and this new set of variables, whichever the new dimensions, these are called as the principal components. Okay, principal components. How we are doing it? The principal components are uncorrelated. There won't be any correlation between the first principal component and the second principal component. Principal component is the dimension. Principal component is the new dimension, transformed, extracted dimension. Okay, there won't be much correlation such that you have to extract these principal components, and which are ordered so that the first few retain most of the variation. And the we will be ordering the principal components. The principal component that is giving the maximum variation will be in the first. Like that, we will be obtaining some k principal components and all. Let us see the algorithm in detail. By seeing the algorithm, we will get to know all these points. Okay, what is this ordering and all? Okay, so definition and derivation of principal component. Now we will see the definition. Okay, so here they have considered x random variables. Okay, x is a vector of p random variables. Okay, we have got p dimensions. Okay, and the variances of the p random variables. Okay, so these two things are given, and the structure of the covariances are correlations. Correlations means how these dimensions are correlated with each other. Okay, correlated with each other. For that, we have to find the how two features are correlated. Okay, so for that, we have to find the mean of each variable, and then we have to find the variation of each value of that variable from the mean and all. Okay, a positive covariance means that these two variables are uh, uh, these two variables are moving in a I mean, if one variable increases, the other variable also increases, something like that. And negative covariance means that when one is increasing, the other variable will be decreasing. Okay, so when we are given, I mean, we have got p dimensions, p random variables, in the sense p dimensions. Let us take a simple example we will consider. Yeah, simple data set we will consider. Let us take age age as one dimension, and then age as one dimension, and salary as another dimension. Okay, and then student, his education qualification as another dimension. So how many dimensions are there in this case? Three dimensions are there. Okay, three dimensions are there. And if we consider even more dimensions, then we need to reduce the data. Okay, high, when it is of high dimensions, applications will be like biomedical sequences, images, videos. For these application data sets, we will have huge dimensions. Okay, so yeah, in that case, we will be using this PCA, principal component analysis. So what you have to find, you have to obtain a new data set with a reduced dimensions, but still we have to preserve the variation of the data set, isn't it? Variation of the data set has to be still preserved. Okay, so for that, let us say this 1 by 2 p into p minus 1 correlations are there, right? So to find the variances, for first variable to the next variable, you have to obtain some covariance. And for second variable, I mean, first variable to all the n minus 1 p minus 1 variables, you have to obtain the covariance. And for second variable to all p minus 2 variables, you have to obtain the correlations or the covariances. Okay, so then you will be finding the variances of the data set. But practically, that will sum up to all these covariances sum up to p into p minus 1 by 2, which is not practically feasible. If you take some millions of attributes, in that case, it is not practically feasible. So an alternative approach, okay, is uh, uh, is to preserve most of the information given by these variances and correlation. This PCA is an alternative approach. Okay, so with the what to say, excessive thing, we have to find the covariance or the relations between p into p minus 1 by 2 a time between those many covariances you have to find. Okay, so in order to avoid that, we are going to PCA. PCA is principal component analysis. Okay, So here it does not ignore covariances and correlation. It concentrates on still here also PCA also does the same thing. Okay, PCA also will be using the covariances, but we will see how it will be handling it. Okay, yeah. So let me go to an example first, and with that example I will explain you. Okay, I will come back to this these slides. Okay, first let me start an example. Okay, so see this thing. Okay, so this is a two-dimensional data sets, right? These are the points in the data set. Okay, this is one point. So 6 points are there in our data set. Okay, 6 points are there. Now you want to do some two dimension. It is a two dimension. This is a one dimension, and a y-axis is another dimension. Two dimensions are there. Now you have to find the, you have to do this, you have to reduce the dimensionality using PCA. Then what you will be doing is, yeah, preserving the variance in the data set. The variance in the data set has to be preserved. Okay, so what you have to do is, first you find the mean value of the x I mean one dimension, and mean value of the y dimension. Okay, and then center these data points. Okay, center these data points at the mean. So yeah, uh, yeah, so after doing a we have centered, see, earlier the data points is like this, isn't it? And now we have computed the mean value and made the mean value as origin. Okay, now the data points has transformed like this. But still but still if you see, their relative position has not changed. Okay, their relative position has not changed. Okay, we have just moved the data points to the mean as the origin. Okay, and then yeah, next you have to find the principal component. Principal component is a dimension, right? So what we have to do is, see, try to fit a line going through the origin. So how this origin, this line has to be is, this line has to pass through the origin, and then this we are starting with a random. So what is principal component? Principal component is a, this line itself is the principal component. Okay, this line is the principal component, but we will be initially, we will be starting with a random line we have started. And then what you have to do, yeah, and this random line is passing through the origin, right? And now you have to rotate the line such that these distance, sum of the squares of the distances will be minimum. So see here, yeah, I will tell you. Yeah, see here, this point is projected here, isn't it? This point has been projected here, and this point is also projected here, and this point is also projected here. And similarly these points are also project all the points onto the this random line. Okay, and then if you see here, uh, these 2 points, if you see these 2 points, there is no much variance. But if you see in this here, there is variance between the 2 points, right? And here also these 2 points, if you see, there is no variance at all. When we project it on this line, we have to, in out of this infinite number of lines, infinite number of lines are possible which are passing through the origin, isn't it? Out of these infinite number of possible lines, you have to pick the line that is giving the maximum variation. Okay, it is an optimization problem that is giving the maximum variation. So if you see here, so many lines are passing through the origin, right? Okay, maximum variation in the sense, when you project these points onto that line, the way the point should not be very close. There has to be some variance. The variance has to be preserved. Okay, now that line has to be selected. Okay, so that line has to be selected. Now see here, yeah, we have started with this, and then we have ended up with this thing. If you see this thing, this line is giving the maximum variance. between the projected points. Okay, now maximum variance between the projected points. Now what we have to do? Okay, first start with a random line and then rotate it passing through the origin, and then rotate it such that the distance, the project I mean the distance from the data point to the projected point has to, some of the squares of the distances has to be uh, maximum. Okay, some of the squares of the distances has to be maximum. Okay, yeah. So these are the distances I1 square plus I2 square. These distances are I1 square and I2 square are the distances from this center, from the origin to the projected point. I1 square represents the distance from this to this thing. We have to maximize this distance. Maximize this distance in the sense minimizing this distance. Okay, maximizing this distance is equal to minimizing the distance, because it is a once again a right angle triangle. And yeah, so maximizing this distance is equal to minimizing this distance. Okay, so and then after that, okay, yeah, so now you have to find the equation of that line. Okay, na? Equation of that line. So here we have the concept of eigenvectors and eigenvalue. Okay, eigenvector is the this one, it is the slope. If you see, the slope of this line is for 2 units of variation in x-axis, there is once again 2 units of variation in the y-axis. Slope is 1. Okay, na? Slope is 1. Okay, yeah, and then what we have to do is we have to make it as a unit vector. Let us say the slope is um, let us say if the slope is uh, yeah, 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 if you see here, for 2 units of change in x-axis value, we have got 4 units of change in y-axis value. Okay, slope is 2 by 4, isn't it? 2 by 4 in the sense 1 by 2. Okay, 2 by 4 in the sense 1 by 2 in this case, and in the previous case it is 1. For a two units of change in x-axis, we have got 2 units of change in y-axis also, so slope is 1. In this case, slope has become 1 by 2. 1 by 2, 1, 2. Okay, this is 2 and this is 1, right? So this value, this distance will be square root of 1 square plus 2 square. So it will be square root of 5. And when we want to make that as a unit vector using singular value decomposition, then we have to divide square root of 5 by square root of 5. All these values, this value also you divide it by square root of 5, this value also you divide it by square root of 5. So we will be getting 1 by square root of 5 comma 2 by square root of 5. This is the principle. These are the eigenvectors, and there is an eigenvalue. Eigenvalue is the sum of the squares of the distances of each distance of the data point from the, I mean, projected point from the origin. Okay, sum of the yeah, let me show you that. It is the sum of the squares of the distance, these distances, where I1 equal to from the projected point to the origin. Okay, that is the eigenvalue, and these are the eigenvectors. Okay, eigenvector, eigenvalue. And what is principal component? Principal component is the mm, eigenvector transpose of the eigenvector times the feature vector. Okay, that is principal component. Okay, first principal component. And next you have to find the next second principal component. Second principal component, we will be in the definition we have seen in the first two slides, we have seen that they are no, that they are uncorrelated. Each principal component is uncorrelated. Okay, so that's why we will be taking a perpendicular one. Orthogonal orthogonal principal component, PC2 will be orthogonal to PC1. Okay, so this component this one, and there is no need to rotate and see and all. This will be perpendicular and it is passing through the origin. That's it. Okay, and now how to find the principal eigenvectors and the eigenvalues, isn't it? Eigenvalue will be the project. We have to project each point onto this PC2, each point on this PC2, and you have to find this distance, square the distance, and do a summation of all such a distance, squares of the distances. That will be the eigenvalue, and the eigenvector will be the slope. You have to find the slope of it and make a unit vector. Okay, like that you will find the eigenvectors and the eigenvalues, and then the PC2 will be the transpose of that eigenvalues times the actual feature vector. Okay, so yeah, and then next PC3, we can find PC3 also. But as it is two dimension, we can find up to PC1 and PC2. That's it. And when it is n dimension, we can find up to n principal components you can find. But here there is a but what is the point if you find two principal components, right? So now see this example. Okay, there are 100 dimensions are there. 100 dimensions are variables, attributes, features all mean the same, right? So for the eigenvalue of PC1, let us say we have got it as 36. Okay, na? And eigenvalue of PC2, we got it as 6. Okay, I will explain all the formulas, but let us see the example first. Eigenvalue of PC3 equal to 2. Like that we have got. Okay, and then see here. Dimensions, how many dimensions are there? We have got 100 dimensions, right? So yeah, and then see here, we are dividing each of this principal component by 5. Okay, for this example we have taken n value as 6, so it is n minus n minus 1, so it is 5. So this is 71 I mean we want to see how much variation each principal component has contributed. Okay, how much variation each principal component has contributed. So 36 by 5 is 7.2, and the total value is 8.8. So how much a principal component 1 has computed is 7 by 2 by 8.8. So 81% of the variation of data is captured by PC1 itself. Okay, you got this point, right? So 81%, and PC2 it has captured this value 1.2 by 5, 8.8. So 4% it has captured. Okay, 81 plus 4, 85% has come already. And then the third, if we go to the third, then it will be 0.4 by 8.8, right? So like that we have to go up to something like 90%, depending upon our application. Depending upon our application, we have to go to that extent, such that 100 dimensions are there, and we are stopping at, let us say I want only to capture the 90% variation of the data. Then first three principal components will be sufficient. From 100 dimensions, we have taken only three principal components with preserving 90% of the variation. Okay, now, so yeah, now we'll go to the formulas, and we will see that mathematical notations and all. Okay, so yeah, if you have any questions, please unmute your mic and you can speak. Okay, so now see this, you correlate example with this mathematical notations and all. Okay, so yeah, although PCA does not ignore, yeah, covariances is there, but how covariances is there, we will see that. Okay, for a linear function, PCA means what? Principal component analysis means that line is once again it's a linear function, right? So it's a linear function of what? What is this x? X is a vector of variables, p random variables we have, right? Small p random number of variables are there, right? And what is this alpha 1 transpose? Alpha 1 is the eigenvector of first principal component. Okay, now we will correlate these two things of elements of X having maximum variance. Okay, where alpha 1 is the vector of p constants. Okay, so alpha 1, these are the eigenvalues, alpha 1 1, alpha 1 2 eigenvalues, right? We will see how we will be correlating these things with the eigenvalues and all. Okay na? So yeah, see here, our objective is to find this alpha 1, that is the principal component. Okay, principal component 1, first principal component we have to find. First principal component will be how many features are there? P number of features are there. It's a linear combination or linear function of this p number of features. So for these are the weights. Okay na? Alpha 1 1, alpha 1 2, you can think of them as the weights. Okay, so now we have to find the alpha 1. Alpha 1 prime is there, right? The prime indicates just the transpose of the vector. Okay, now how to find that? Yeah, so before we will see how to find that, but before going that, the next pc principal component is alpha 2. Alpha 2 is the next principal component. Alpha 2 is once again similar to something like this, alpha 2 1 x1 plus alpha 2 2 x2, something like that, right? So next principal component. Okay, and one more thing is that that a principal component has to be uncorrelated with the first principal component. Okay na? Uncorrelated, like that you have to get. And then having maximum variance while preserving the variance. Okay, like that you have to go up to k principal components like alpha 1 transpose x, alpha 2 transpose x, like that you have to go up to k principal components and the kth principal component. So this is the kth principal component, right? Alpha k
They've got
is
some
the kth
step-by-step
principal
guides on
component,
how to
and
get
that
started.
has
So
to
if I
be
want to actually stream out this awesome production, I need to go into the
with
streaming
all the
settings
k
and
minus
set
1
up my
principal
stream.
components,
In
and
vMix,
it
your
has
streaming
to
settings are located in
preserve
the
the
bottom of the
variance.
interface.
Okay, so they
Just
are
click
saying
the little
maximum
gear
variance and all.
icon that's
Preserve
next
the
to the
variance to the
stream
maximum
button.
extent
So
possible.
this window allows you to set
Okay,
up your stream
so that's
or
why
make any changes to
initial
existing streams that
slides
you've
we
got
have
set
seen
up.
some ordering,
Now
right?
you'll notice up the top there's a
Ordering.
profile
That
section.
order
So
is
once you've actually
first
set up all
principal
of your
component
streaming
is
information,
preserving
you
the
can save
maximum
it as a
variance.
profile.
Like
Now
in
for
the
those
example
people
we
that are
have
doing
seen
multiple
88%
productions,
or
it's
something,
really handy to be
82%
able to
something we
save
have
all
seen,
of your
right?
different settings
Next
and just
principal
switch between them
component is
if you need
preserving
to.
some
So once we've set up
4%
today,
or
we can
something
add
like
a
that.
new
So there is an
profile that we've
ordering,
got.
right?
So
Okay,
underneath that, you'll
next
see the
see
1,
this.
2, and 3, and
Kth
this refers to streaming to
derived
multiple
variable
locations. Because we're doing
is the
a
kth
basic
principal
tutorial today, we're
component.
just going to
Okay,
show you how to
up
stream
to
to one
p pieces
location,
we
but you can
can
check out the
find up
video in
to
the description on how to
p
stream to
number of
multiple
principal
locations.
components. But
Now,
if
as we
we
mentioned
once
before,
again
there are
find
a
the p number
ton
of
of
principal
different
component,
streaming
then there is no
providers out
point
there,
of
and the
dimensionality
list seems to be
reduction, right?
growing every
So
day.
we will
Now,
in the
we've added
example
some
we have seen
direct login
100
access
dimensions
to a
are there,
bunch
but
of different streaming
we have
providers.
taken only
So we've connected up to their
three
API,
dimensions,
and it
isn't it?
allows you to
Three
log into
dimensions
your
only we
streaming
have.
account
I mean,
directly
three
through the
pieces
vMix
only we have
interface.
considered with
So as you can see from the
and
list, we
these
have a lot
three
of different
pieces are
free
preserving
providers,
about
including
90% of the
Facebook,
variation of the
YouTube,
data.
Twitch,
Okay,
Periscope, and we also have some
so
paid
no
providers
need
as
to,
well,
even though
such as
you can
Vimeo,
compute
Wowzer
up to
Cloud,
p
Ustream,
principal components,
IBM,
no need to
Guitars,
go up to p.
StreamSpot,
Okay, you can
and
stop
that
it.
list gets added to all
Where
the
m is
time.
less than or
If you don't
much
see
less
your
than,
provider's
far
name
less
on the
than
list,
p.
you can always get them
Okay,
to
having
contact us
defined
and we can look
pieces.
at adding them to
Now
this
we
list.
need to know how to find them. We have
Now, if
defined
you
how
don't
the
currently
pieces
have
has
your
to be.
provider's
What
name
is
on
the
this
definition
list,
of the
that's no
pieces?
problem
It
at all.
has to
All you need to
preserve
do
the
is select
maximum
Custom
variance, and it is a
RTMP
linear
server.
combination.
Now, every
And
streaming
once
provider will
again,
give you the
it
ability to
has to be
stream
correlated,
by using a stream URL and a
uncorrelated
stream
with the
name or key.
all the previous
So it's just a
pieces,
matter of
and a
copying
maximum
this bit of
variance it has to
information
preserve,
into
right?
vMix in the URL
So
setting, be able to stream on
yeah,
Facebook, LinkedIn,
now
and you can start streaming.
they
Set
have
quality.
taken the covariance
Now, a lot of the
matters.
time, streaming providers will
Covariance
give you some
matters. Okay,
guidelines
consider
as to
for
the
the
best
moment the
streaming
case
settings
where
for
the
their
vector of
platform.
random variables
If that's the
has
case,
a known
then use those
covariance
settings.
matters. Now
For
we
example,
will see
places
how
like
the covariance
Facebook,
matters display.
Periscope, Twitch
So
will
how
give
many
you kind of
variables
some
are there?
guidelines as to
P number
stream
of variables
how
are
to
there.
stream.
So
So
P by P.
we've added
P
some
by
of those
P is the size
presets
of
here
the
in vMix.
this is
Now you can
covariance
choose one of
matrix
these
and
presets to stream
covariance
to.
of
Like we have
x1.
today, we've
So
chosen
this is the first
1080p,
feature
3
and this
megabit.
is the first feature
But if we want
itself.
to actually make any changes
Covariance
to the
between
settings
x1
of this,
x2,
all I need
covariance
to do
between
is click
x1
this.
x2, I mean x1 x1 and x1 x2, x1 x3, like that you have to find the covariance between each possible each possible combination of attribute pair. How to find the covariance? I will show you the formula. Yeah. So covariance formula x comma y is there, right? Find the mean of the first variable, mean of the second variable, and for each you have to find the difference of each value from the mean, and you have to take a product of it by n. What is n? Is the number of samples in our data set or the number of examples in our data set. Okay, so with that formula, you will be finding the covariance matrix. Okay, now this matrix you have got. Okay, so the description is given here. This is the matrix whose ith comma jth element is the covariance between the ith and the jth element of x. Okay, all these things we know. Okay, so when x and x1, I mean, when this I equal to j, in that case, what happens when I equal to j? It becomes variance. Variance means x minus x bar. X bar is the average whole square, isn't it? That is the formula for variance. When I equal to j, it become variance. Rest all time when I not equal to j, it is the covariance itself. Okay, so yeah, next. Yeah. So we have the covariance matrix defined, and we have the till now we have defined the principal components. And this covariance matrix we are defining with the sigma. Okay, na sigma. This is the representation,
Notes
replacing by a
small, not
small
until points.
covariance matrices. Okay, na.
40 points, not until
Next.
notes of
Yeah,
volume.
for
What are
k
there?
equal to 1, 2, and so on up to the kth
Right?
PC is
You are
given by.
considered right?
So how we you
Balance
already
balance.
know, we have already seen this representation, right? This is the kth PC. Alpha k is the kth PC. So what they are saying is alpha k is a eigenvector of sigma corresponding to the kth largest eigenvalue lambda k. We have seen it, right? We have seen the eigenvalues in our example. Eigenvalue is the sum of the squares of the distances of the projected point from the origin, isn't it? That is the eigenvalue. And what is the eigenvector? We have seen in the example. Eigenvector is SVD, single value decomposition. We have found the eigenvector as the slope and all, right? From the slope we have determined the eigen vector, right? So yeah, so here what they are saying is this alpha k is the eigenvector of sigma. For sigma, when you compute the eigenvector, that will be shown later, that derivation, how it will become the eigenvector of sigma and all, the derivation is there. But as of now, uh, this alpha k is the eigenvector of sigma, and it is corresponding to the largest eigenvalue lambda k. Okay, how it is we will see. And then if alpha k is chosen to have unit length, we have seen that, right? Unit length. Alpha k is unit length in the sense we have made it to unit length, right? We have divided it by square root of, a square plus b square, like that we have done, right? All the values and made it using that is called singular value decomposition and all. Okay, so this condition, so unit vector in the sense, when you do a matrix, multiplication of that matrix along with its transpose, we will get one. We'll see an example once. It will give you more clarity. In that example, we have got this, right? 1 by square root of 5. Yeah. Yeah, 1 by square root of 5 comma 2 by square root of 5. And this is the vector that we have got, right? And then see, if we multiply this transpose of this vector, transpose of this vector with that vector itself, 1 by square root of 5, uh, 2 by square root of 5, and its transpose. Okay, so you will get a unit vector. Okay, you will get a unit vector. Yeah. Yeah, now coming to, it will be 1 by 1 matrix, right? It will be a 1 by 1 matrix, and you will get its value as 1. Okay, na? So now, yeah, see this. Then, yeah, then a variance of zk. So if we find the variance of zk, that is equal to the eigenvalue, where this denotes the variance of zk. Okay, now we will see how it is derived. Now they are talking about how to derive the form of PCs. Okay, consider first alpha 1 transpose of x. The vector alpha 1 maximizes, our objective is to maximize the variance, right? Maximizes the it has to maximize the variance. So variance is alpha 1 transpose of x. That variance equal to alpha 1 of transpose of x sigma covariance. This is the covariance, right? Covariance times alpha 1. So our objective, we have to find the principal component 1. To find the principal component 1, it has to maximize the variance. Maximizing the variance means this term has to be maximum, and it has become an optimization problem. This term has to be maximized. Clear that as it stands, the maximum will, and this is sigma is the covariance matrix, right? Maximum will not be achieved for finite alpha 1, so a normalization constraint. So they are using a normalization constraint. This is the constraint, right? Alpha 1 transpose of alpha 1 equal to 1. Okay, the sum of the squares of the elements of alpha 1 equals to 1. Okay, sum of the squares of the elements of alpha 1 equals to 1. So they have used this normalization constraint. Okay, objective is to maximize this subjected to this constraint. So maximize subjected to this constraint, and we are using Lagrangian multipliers. Lagrangian multipliers to solve this optimization problem. Now finding the PC. First PC has transformed to an optimization problem, right? Optimization problem. Our objective is to maximize the variance while subjected to the normalization constraint. Okay, so now see here. Okay, so using Lagrangian multipliers, we are solving this optimization problem. So this content has to be maximized, and the constraints, this is the constraint, right? Alpha 1 minus 1. So lambda, they have introduced lambda as lambda is a Lagrangian multiplier, and when we are finding the derivation with respect to alpha 1 transpose, we are getting this equation. Okay, na? Sigma minus alpha ip. What is this ip? Ip is an identity matrix of size p by p. Okay, alpha 1 equal to 0. So now if we see this, lambda will be the eigenvalue, and alpha 1 is the eigenvector of this covariance matrix. That's why we are saying eigenvector, eigenvalues and all. Okay, so finding the so now we have got some connection, right? So we have to find the principal component, that is maximizing the variance in the sense, this is the component that is maximizing. This is the covariance matrix, and this is the component. It has to this value has to be maximum subjected to this constraint. So we are using Lagrangian formulation for solving this optimization problem. And so we have in that method, Lagrangian algorithm, we will be using this Lagrangian multiplier, differentiating with respect to alpha 1 transpose and equating it to 0. Then we will get the maximum value. By solving that, it has taken something of this form, where if when this is of this form, when when the problem has come to this form, the lambda will be the eigenvalue of this covariance matrix, and alpha 1 will be the eigenvector. So now what has happened, we have Yeah, so and we are saying that lambda 1 is the largest eigenvalue of sigma. Okay, because our objective is to find the maximum variance, right? To decide which of the p eigenvectors gives this with the maximum variance, note that the quantity to be maximized is this is the quantity that has to be maximized. Okay na? So lambda must be as large as possible. Okay, lambda has to be as large as possible. And then thus alpha 1 is the eigenvector corresponding to the largest eigenvalue of sigma. Okay, and variance, if we take the variance, okay, variance equal to lambda 1, this is the variance is the squares of sum of the squares of the distances of the projected point to this origin. Okay, that is the variance. Okay, we have seen the eigenvalue, right? We have there our objective is to maximize that variance, isn't it? Maximize that variance or to minimize the distance of the data point to the projected point, either to minimize that or to maximize this or to get a maximum value of the projected point to the origin, isn't it? So yeah, yeah, now we have found the by this time we have found the eigen vector corresponding to the principal component and the eigen value corresponding to the principal component 1. Now we have to go and this first principal component, how to find I mean how much variation it is preserving. We have seen, right, some 80% of variation of the data set is preserved by first component, something like that, right? We have seen the formulation. We have to find the, what to say, find the uh, ratio between the total variance, I mean that particular principal component and with the total variance, then we will get the contribution made by the principal component 1 and all. Okay, now we will see how to derive the second principal component. Alpha 2 is the second principal component. Once again, it also has to maximize the variance, right? So this is the variance component. This component has to be maximized. And what is the constraints here? This PC2 has to be uncorrelated with the first PC1, with the PC1. Okay, so see here, covariance of this PC1 and the next PC1, first PC1 and the next PC1 has to be 0. They both of them has to be uncorrelated. And third PC has to be uncorrelated with the two PCs, like that. Okay, denotes the covariance between the random variables x and y. Okay, now see that this is the constraint we have. This is the constraint we have, and this value will be once again alpha 1 transpose sigma of alpha 2, and this sigma is alpha this sigma is alpha 1, and then this is the constraint. This is the constraint here. Thus any of the equation that a correlation has to be 0, right? When we make this to 0 or this to 0 or this factor to 0 or this factor to 0, because lambda 1 cannot be 0. This product can be 0 or this product can be 0. Okay, could be used to specify 0 correlation. Any of these conditions, you can use any of these conditions to specify that there is a 0 correlation between PC1 and PC2. Okay na? So yeah, choosing the last one, they have chosen this one, alpha 2 transpose of alpha. And then once again they are solving this using Lagrangian. So objective is to maximize this and subjected to these two are the constraints, right? These two are the constraints. Once again this is a unit value, right? So you might have remembered this unit value.
The
Okay,
tremors in the
so
spear shaft.
and this lambda is
I
once
craft
again
my
an
ways through
Lagrangian
blazes
multiplier.
of fire
And what is
steams,
this?
absorb
This
the
is
failings of deadened
equal to
ends
0.
to
This is
render the
another
floors I
constant.
dance upon.
Pi and
I am the
lambdas are both
spaces
are
between
Lagrangian
applause,
multipliers. So
the
two
wars
constraints
of
are there.
hearts running
Here
through
one
heaven's
constraint is
halls.
that
I breathe the
it
forms
has
of light and silence,
alpha has to
extol
be
the
a
course of
unit
cosmic
vector.
riots.
Alpha
I am
has
the
to be a unit
glory
vector, and
of the
another constraint is
giants Manassu,
principal component 2 has to be
Sagarmatha, watchmen of the
uncorrelated with
Asian
principal component
plains.
1.
They
That is another
yield my
constraint, right?
name,
So
made famous through the
two
cries of
constraints they have
albatross
introduced,
flocks,
and
inflamed in
this is the
Pacific
component
fires.
that has to be
I am
maximized.
dressed in the
Variance
spray of
component that has to
Nevada
be maximized.
dunes,
And then
clothed in the shadows of
derivating this thing with
Sahara
respect to
caves.
alpha
I
2
am the
and
light of
equating it to
lunar
0,
flames,
we will get
fresh in the rains
something
of
like this. Okay,
Amazonia.
now? And
I paint the
multiplication on this
trains of
on the left by
Antarctic
this gives
quests,
something like
release
this. And
dominion to desert
we have
Panthera.
this thing,
I
right? Alpha 2
authorize the
transpose of
remains of
alpha equal to
Aztec and Inca that
alpha 2
bloom through the
transpose something.
visions of
Okay,
mountain
which
tribes.
since the first
I
two
ride
terms
the
are 0
skylines,
and
breathe the
this equal
signs,
to 1
ignite the paths
reduces
of
to
astronomy's eyes.
pi
I am
equal
the
to 0.
unheard,
Okay, pi is
heard in the
equated to 0.
storms that
And
burn
then
on
once
my
again, if we
words.
see,
I am my
different
heart
principal
broken
components.
and
Among
awake.
the
I
k
am
number
the
of principal
watchman of
components,
your
select the
sleep.
first
I
principal
wait
component
and
such
wait
that
till the shaking
this
cease.
this principal component will represent
I am
the
the truth
original
they
data
call
set. This will
release.
represent the
When the
original data
darkness
set
flares
with
and starts to
while
speak, I
preserving the
sculpt the shades of
variance in the
daybreak.
data set.
It is
Okay,
me you
with
seek.
this I will end my session. If you have any questions, you can unmute and you can ask. Yeah. Yeah, if you have any questions, please let me know. Or otherwise, I am done with my session.